Now let's nerd out with some functions in Python and see some examples that we can dive into. So for our first example, we have a simple function. We know it's a function because we have the def keyword to define a new function, and we have the function is named roll_die, and it has no function arguments or parameters. And we see a colon and everything else indented. And we see roll is equal to random.randint 1, 6, and we return roll. So a description of this function is I'm going to say that this function returns the result of rolling a 6-sided dice or die. So if I do this, I'm going to be able to test this function by simply saying roll_die, and that will call this function, and roll_die is going to have no argument, so I have to have open close parentheses just like I have in my definition. And Carly, if I run this function that you just typed up, what do I get? Do I get a 1 through 6?
I get a 6.
Awesome. And if you roll it again, do you get another ramp value?
Roll again, 1.
Awesome. So we see we have that range of values between 1 and 6. Now in example B, we see the function change in just a small way. We have def roll_die, so it's the same roll_die function, but now we have a function argument or parameter called sides. So this is going to be an input that we're going to be required to give to the function. And we say roll is equal to random.randint 1, sides, and then we return roll. So this is going to be, I'm going to describe this as returns the result of rolling a sided die, where we're able to decide how many sided die we give. So if we just call roll_die with open and closed parentheses, we should get an error because we know that this function requires one parameter.
Yes, it says roll_die is missing one required positional argument, size.
So we need a parameter or an argument to this function, and we can go ahead and say, I want to roll, let's do something crazy. I want to roll a 1,000-sided die.
Crazy. I got 720 when I rolled the first time, 823 when I rolled the second time, 186.
So we've got a 1,000-sided die. So now let's see some more complicated bits. So an additional complicated bit is that we have roll_dies. Now the only change we're making is we're saying sides is equal to 6. So the function otherwise the same, except for what we're giving is we're giving the function parameter, or the function argument, a default value. So this is going to be the default value if we don't specify the value. So I can say the description of this is this is going to be returns the result of rolling a sided die defaulting to 6-sided. So it defaults to a 6-sided die. So when we run this function, and we have this function known by Python, what's the result of just doing roll_die with nothing inside the parentheses?
So I got a 1.
So we got a 1, and let's do a few rolls to see kind of what the range is.
Another 1.
Another 1.
A 3.
3.
Another 3. 5.
5.
2.
So I'm pretty convinced that this looks like a 6-sided die.
Yep.
That we're getting values in the 1 through 6 range. We didn't get any 6s, but that's a pretty low probability of getting a 6. But we got most of the other values. So now let's try the same function. We're not defining a new function. We're just using now roll_die of 100.
I got 22.
22.
71.
71.
95. 6.
So this again looks like a dice roll that's between 1 and 100. So this is great. So what we have is we have one function that can work as a default dice, 1 through 6, as a standard dice, just like what we've been using all series long, but it can also be modified, and we can pass that parameter to make it do something different. And this is going to be a common theme we see in Python, is almost all functions in Python have default values that are the usual values that most people use. And then we can have these special values that we specify when we want to change something from the default. So let's do a slightly more complicated example. Here I have a function. Let's see what it's going to do. So this function is def spin, and it has no function arguments or parameters. And it says spin is equal to random.random -1, 32. Interesting. So this is going to create the value -1, 0, 1, 2, 3, all the way up to 32. And it says if spin is equal to -1, it's going to return 0, 0 green. And if spin is double equal to 0, it's going to return 0 green. If spin is mod 2 is equal to 0, so this parenthesis operation is a mod operation. This is something we haven't seen yet, I don't think.
Yeah. Also, wait, before you continue, elf?
Elf, yes. So one thing in Python is we often want to chain conditionals together. So we could write else : if : and have a lot more text to kind of write these conditionals, these else statements. We can chain a number of else statements together by using else if or elif. So yes, we have this if, elif, and else.
Got it.
So we have a chaining conditional. It's going to go into only the one that it matches, and it's going to skip all of the others. So if spin is equal to -1, we return double 0 green. If spin is equal to 0, we return 0 green. If spin modulo 2 is equal to 0, which means if I divide the number by 2 and the remainder is 0, then it's going to go into this. And I have a comment right here that helps me explain what this is doing, since this is kind of a weird line of code. This says if it's an even number, because we know if we divide an even number by 2, you're going to get a whole number back. It's going to remainder is 0. And then it's going to return an f string, and it's going to return the value. So f string allows us to put a variable in there. So the variable is spin inside curly brackets. So f quote curly bracket spin. That spin variable is the variable that holds my result. So for example, if my result was 4, this is going to return 4 black. Else, this is going to be all of the odd values. We're going to return an f string of the spin value. So the spin, if it's an odd value, it's going to be something like 3. So 3 red. So I see that basically a -1 result is going to return 0, 0 green. The 0 result is going to return 0 green. The 1 result is going to return 1 red. The 2 result is going to return 2 black. The 3 result is going to return 3 red. And going all the way to 32, which 32 is an even number, so that should return 32 black. So what we want to know is we want to have a description of this function. So what we've done so far is we've went through and understood what this function did. So Carly, greens, blacks, reds.
This kind of sounds like roulette.
Yeah.
My favorite gambling game.
So this is a description of a spin of a standard US roulette wheel. So every time we call roll, we are basically playing a game of roulette and seeing where the ball lands. And this function is going to return us the number dash the color. So this is really useful. So Carly, were you able to grab this function?
Yes. So I went ahead and typed it, and it looks like nothing happened when I ran the function, and I will do spin.
Yep. So now we're going to call the function spin. It has no arguments. So we do spin, open, close parentheses.
And I got 23 red.
Awesome. So 23 red. So I'm going to take a gamble. I'm going to bet 52 cards on black.
How about $52? I'll spin again. 22 black.
Oh, I'm a winner. I've doubled my cards. That is awesome. So should I go double or nothing?
Yeah.
Okay, I'm feeling double or nothing for red.
For red. Should have stuck with your original black because it's 10 black.
Oh, I've lost everything. Congratulations.
Thank you.
Casino's rich. So we have one last example. So what you saw there is we have now a function that plays roulette. So we can obviously add this to part of a simulation and start thinking about casino games as simulation, because now we've got all of that there. So the last function we have here, part E, is def sim roll 6. So this is a sim roll 6. It has one function argument called rolls that has a default value of 10,000. So if we simply have 10,000, if we don't give her any arguments, it's going to roll it 10,000 times. And we see inside this function, we have a simulation. So the simulation says data is equal to an empty list, And then for I in range rolls, so it's going to roll however many times. So by default, it's going to roll 10,000 times. Then roll is equal to random dot rand int 1 comma 6. So this rolls a standard 6-sided die. It accumulates roll into the variable d, and then data dot append roll. Outside of that for loop, it says df is equal to pd dot data frame of data. And then it returns the value that this function gives back to us is it returns the length of the data frame where df.roll is equal to 6. So the length of the data frame where the roll value is equal to 6 basically means how many times in 10,000 rolls did I roll a 6. So I'm going to write this description. So this function returns the number of times a simulation of rolling 10,000 dice, returns the number of times a simulation of 10,000 dice rolls a 6, where rolls can be modified to be a value other than 10,000. So we can roll 10,000 dice by default, or we can roll just 2 dice or 100 dice. But by default, we have 10,000 dice. So Carly's been typing up this function, and it looks like you have an error.
I have an error. It says data is not defined.
So it looks like inside of this function, data is equal to square brackets should be the very first line, making sure it's tabbed over from the function.
I think this should be data.append d.
Oh, you're totally right.
I think that's the problem.
Data.append d appears right here.
All right, and that seemed to fix it.
So, Carly, did you ran this? Did you get any errors?
No. So I'm going to look at my data frame really quick.
So we're not even going to see a data frame because this returns the length of the data frame.
You're right.
So what's the expected? So I'm going to just think about purely statistics.
Yes.
So Carly, using this definition, 10,000 dice rolls, we are counting the number of times we get a 6. If we do sim roll 6, we're going to do 10,000 dice rolls. So just doing pure statistics, how many times do we expect to get a 6 when we're rolling 10,000 times?
So it should be 10,000 divided by 6.
So 10,000 times 1 out of 6 rolls. So 10,000 divided by 6 is going to be what, like 1,800?
1,666.67.
So 1,667.
Yep.
Rounding up to the 7. And then, so that's the expected value. And then if we actually run this sim roll 6 die, or sim roll 6.
And I got 1,687 sixes. So pretty close to what we expected.
Yeah, 1667 is what you thought we'd get, 1687. So we have really high confidence this function's doing exactly what we want.
Exactly.
But it may be that we didn't get the exact value that we thought we were going to get. Maybe we got a value way different. So then we'd want to investigate more and see if our function's right, see where an error might be in the logic. So what's the expected result of sim roll die 1? So first, thinking just about the statistics of this. So if I roll 1 die, what's the expected result of rolling 1 die?
Of getting a 6?
Yeah, it's still only 1/6 probability,
yeah,
right?
1/6 probability, so you're expected not to get it. It's closer to 0 than it is to 1.
Yeah, the rounded expected value is 0. I'm going to get 0 more often than I get 1. So if I do sim roll die of 1, this should modify this function, only roll a single die instead of rolling 10,000 die.
And I got 0.
You got 0. So we have a function that used to return 1687, it's now returning 0. And we can now roll any number of dice for any different outcomes. So we can say we have 20 dice that we want to roll, or we have, like I've got about 100 dice in front of me. So if I were to roll all of these dice at once, Carly, how many 6s should we expect to see?
However many we roll times 1/6.
Let's do the simulation.
Oh, okay.
And do roll dice, and I'm going to roll all these dice, and
you said there's 100?
100 dice.
28.
We should see 28 6s appear on the table. And that's pretty great.
Yeah.
So that's a little bit of functions and how you can build increasingly complex problems by using functions. And now you can start thinking about just, okay, I'm thinking about each one of these dice as rolling a 6, and a single function now does all the work of a simulation. So we're able to build more and more complex problems by taking little bits and putting them into functions and then reusing those functions to build bigger pieces.